Welcome to Selection with Sathi. Today we cover backtracking, a powerful algorithmic technique for solving constraint satisfaction problems. We will learn the general backtracking template, then apply it to n-queens, Sudoku, subset sum, permutations, and rat in a maze. Backtracking is tested frequently in GATE CSE and coding interviews. Let us begin. Let us start with the general backtracking template. The pattern is choose, explore, unchoose. Look at line 2. First check if we have reached a complete solution. If yes, process it and return. Lines 5 through 9 iterate through all possible choices. Line 6. Check if the choice is valid using a feasibility function. Line 7. Make the choice, modifying the current state. Line 8. Recurse deeper with the updated state. Line 9. Undo the choice. This is the backtracking step. We restore the state so the next choice starts fresh. This three-step pattern applies to every backtracking problem. Pruning is what makes backtracking efficient. Without pruning, we explore every possible path in the decision tree, which is exponential. With pruning, we cut entire subtrees that cannot lead to valid solutions. There are three main pruning strategies. First, constraint checking, verify all constraints before recursing. Second, bounding, if the partial solution already exceeds the best known answer, stop. Third, symmetry breaking, avoid exploring mirror or equivalent solutions. For example, in n-queens, checking row, column, and diagonals before placing a queen prunes the vast majority of the search space. The n-queens problem asks us to place n-queens on an n by n chessboard so that no two queens attack each other. Queens attack along rows, columns, and diagonals. We place one queen per row, trying each column. Look at the is_safe function starting at line 4. Line 6. Check if any queen in the same column exists above the current row. Lines 8 and 9. Check the left diagonal going upward. Lines 11 and 12. Check the right diagonal going upward. If all three checks pass, it is safe to place the queen. We only need to check above the current row because we place queens row by row. Let us look at subset and permutation generation, two fundamental backtracking patterns. For subsets, look at lines 3 through 10. At each index, we have two choices, include the element or exclude it. Line 7, include the element, recurs to the next index. Line 9, pop it off, which is backtracking, then recurs without including it. This generates all 2 to the n subsets. For permutations, look at lines 14 through 20. We fix each element at position L by swapping, recurs for the remaining positions, then swap back to restore the original order. This generates all n factorial permutations.
Let us solve 4 queens step by step. Row 0. Place queen at column 0. Row 1, column 0 is same column, skip. Column 1 is on the diagonal, skip. Column 2 is safe. Place queen at row 1, column 2. Row 2, check all columns. Column 0 is on the diagonal of row 1, column 2. All 4 columns are unsafe. Dead end. Backtrack to row 1. Remove queen from row 1, column 2. Try column 3. Place queen at row 1, column 3. Row 2, column 1 is safe. Place queen at row 2, column 1. Row 3, check all columns. All are attacked. Dead end again. Backtrack further. Eventually, we find two valid solutions. Solution 1, columns 1, 3, 0, 2. Solution 2, columns 2, 0, 3, 1. The four queens problem has exactly two solutions. Now let us understand the Sudoku solver concept. Look at line 2, find the first empty cell in the grid. If no empty cell exists, the puzzle is solved. Lines 6 through 11, try each number from 1 to 9 in the empty cell. Line 7, check if the number is valid, meaning it does not conflict with any number in the same row, same column, or same 3 by 3 box. Line 8, if valid, place the number and recurse to solve the next empty cell. Line 10, if recursion fails, we reset the cell to 0 and try the next number. Line 12, if all 9 numbers fail, return false to trigger backtracking. In practice, pruning makes Sudoku solving very fast, typically under a millisecond. Subset sum, find all subsets of 2, 3, 5 that sum to 5. Start with empty subset, sum 0. Include 2. Sum is 2. Include 3. Sum is 5, equals target. Record subset 2, 3. Backtrack, exclude 3. Include 5. Sum is 7, exceeds target. Prune this branch. Backtrack, exclude 2. Include 3. Sum is 3. Include 5. Sum is 8, exceeds target. Prune. Exclude 5. Sum is 3, not target. Move on. Exclude 3. Include 5 alone. Sum is 5, equals target. Record subset 5. Final answer, 2 subsets, 2, 3 and just 5. Notice how pruning at sum greater than target saved us from exploring many branches. Permutations of 1, 2, 3 using the swap approach. Fix 1 at position 0. Now permute positions 1 and 2. Fix 2 at position 1. Only 3 left at position 2. First permutation, 1, 2, 3 swap back. Fix 3 at position 1 by swapping 2 and 3. Only 2 at position 2. Second permutation, 1, 3, to swap back. Now fix 2 at position 0 by swapping 1 and 2. Permute positions 1 and 2, gives 2, 1, 3 and 2, 3, 1. Fix 3 at position 0 by swapping 1 and 3. Gives 3, 2, 1 and 3, 1, 2. Total, 6 permutations, which is 3 factorial. Rat in a maze, find a path from top left to bottom right in a 4 by 4 grid. 1 means open cell, 0 means blocked. Start at 0, 0. Mark it in the solution. Try going down to 1, 0. Mark 1, 0. Try going down to 2, 0. But 2, 0 is blocked. Backtrack to 1, 0. Try going right to 1, 1. Mark 1, 1. Continue right to 1, 2. Go down to 2, 2. Go down to 3, 2. Go right to 3, 3. We have reached the destination. The path is 0, 0, 1, 0, 1, 1, 1, 2, 2, 2, 3, 2, 3, 3. Backtracking handled the dead end at 2, 0 automatically by undoing and trying a different direction.
Quick exam tips. First, always prune early. Check constraints before recursing, not after. This can reduce runtime from hours to milliseconds. Second, draw the recursion tree to understand backtracking. Each branch represents a choice, and leaves are either solutions or dead ends. Third, always define a clear base case and constraint check. The base case detects when a solution is complete, and the constraint check prevents invalid choices. Fourth, for gate, know the time complexities. N queens is O of n factorial, subsets is O of 2 to the n, and permutations is O of n factorial. For more DSA concept videos with code walkthroughs, download the Selection with Sathi app. Like and subscribe. Thank you.